do next one. All right. So it's a great pleasure for me to introduce Shi-ang Qi. He's a fourth-year PhD student in the Department of Computing Science at University of Alberta, and he is in the AMI, so Alberta Machine Intelligence Institute. He's a PhD student of Professor Russ Greiner. Qi's work is on survival prediction, and one of the I don't want to say open problems, but one of the key problems in survival prediction is that of evaluating the models. Okay, so how do you evaluate survival models? So that's a very active area of research, and Shi-ang has fantastic work done on that aspect. So let's hear what he has to say about the topic. So thank you for your time.
Okay, thanks, Alessandro, for inviting me to this seminar. So I'm Shi-ang. Today I'm going to present our last year ICML paper with the title "An Effective, Meaningful Way to Evaluate the Survival Models." So survival analysis is just like regression task. It predicts the time until event. For example, the event could be the death or a cancer relapse or some service subscription or unsubscription. So the data set always usually contains with somebody recruited to the study. And during the study period, we observe some event of interest. So for example, in this figure, it is the death event. And survival analysis is unique due to the existence of the censorship. So for example, the patient 3, the third patient here, he got recruited in the study, and after a while, the administrative people accidentally missed her or his file. So in this case, we can only record it a last time for what last time for her or his file missing. This time will be represented as the censor time, which is a lower bound of the event time, because we know for sure that the event time haven't been happened until this time of the study. Another example would be the fourth people. He recruited in the study and left the study after because due to some for example, the personal reasons he left the country or just don't want to communicate with people. And another type of censor is a person got recruited in the study, and during the study period, we couldn't able to observe any event happening to these people, to this person. At the end of the study, we can only record the end time as the censoring time, which of course is a lower bound of the event time because he must happening the event time after the study. So for every subject in the data set, in the survival data set, we can assume one thing. We can assume everyone have an event time and everyone also have a censor time. However, we can only observe the earlier happening time, which is the minimum of the two. And on top of that, we can observe another thing, which is the event indicator. It is a binary indicator to indicate whether this person's recorded time is an event time or it is a censor time. So in survival analysis, we also usually make one important assumption, which is the independent assumption. The event time and the censor time, we can consider them as a random variable. They will be considered as independent conditionally on the covariance. And this is the example of survival datasets. You see on top of the regular regression datasets, we have the features and we have the time as the label, as the regression label. On top of that, we also have a binary label called event, which it equals to 1 means it is an event happening to the subjects. It equals to 0 means the event didn't happen to to the people, to the subjects during the study. So survival analysis algorithm try to build or try to predict the individual survival distributions. So an individual survival distribution contains survival probability, predicted survival probabilities for all future times. So for example, this time point, this this blue point represents the survival probability of these people beyond time 1 is 69%. And this time point represents the survival probability for these people beyond the time 2.3 is 50%. So this point can be also referred as the median survival time, which is the intersect of the individual survival distribution curve. We can also call it ISD curve, and the 50% horizontal line. The intersect of these two lines, we can represent it, use a diamond here. We call it the median survival time, and we can use it as a proxy for the predicted event time. Another type of proxy for the predicted event time is called the mean survival time, which is the area under the survival distribution, represented as the blue shadow area in this figure. So in this research, the objective is to find out appropriate metrics for evaluate the survival models. So there has been so many evaluation metrics to evaluate the performance for survival models. For example, the concordance, the Brier score, the integrated Brier score, some AUC scores, some calibration scores. We categorize them into 3 categories. So the first one, for example, the concordance index and the mean absolute error or mean squared error, they estimate the accuracy for a point prediction, where the point prediction can be the median or mean survival time that we just introduced. So basically, they estimate between the true predicted time, true time and the predicted times, and see whether the model do good on those predicted times. And another type of the matrix estimates the curve prediction. For example, the integrated Brier score estimates the square differences for those 2 shallow areas. It is the differences between the ISD curves and the heavy side functions. And there, of course, can be some calibration measurements for the whole curve. And the third category is the AUCs, the Brier score, and 1 calibrations. They are all measure the performance of the survival probability at a single target point. So in these 3 figures, our target point is time 2. These brown dashed lines, vertical lines. So we're looking at the survival probability predictions at those times and evaluate how accurate it is. So in terms of the time to event prediction, many people uses the concordance index. The concordance index I can see it is the most dominant metrics in survival analysis. However, one of the discussion in our study, in our paper, is that concordance index, also called C index, is not as useful as somebody may think. So let's motivate this with an example. So for example, we have 4 patients, A, B, C, D, colored with highlighted with different colors. A with blue and yellow for B, green for C, and red for D. And we have their true event time representing as stars, and the predicted ISD curve represented as the curves, of course. And the first thing we're gonna do is we're gonna calculate some useful statistics. For example, the predicted time. Here's the predicted time. We use the median survival time, which again is the intersect between the intersect of the ISD curve and the 50% quantile, 50% horizontal quantile line. Yeah, and we obtain the 4 predicted survival time from the 4 curves. And then the next step, we're going to check for every pair of the data set whether the true orders matches with the predicted orders. So for example, for pair A and B, representing A represented by blue and B represented by yellow. So the true order, the order of stars, the yellow star is ahead of the blue stars. And for the predicted order, the yellow diamonds are ahead of the blue diamonds. In this case, we can see that our model did a correct prediction in this pair. And for the second pair, for pair A and C, the true order, we can see the green is ahead of the blue. And for the predicted order, it's also green ahead of the blue. In this case, it's also a correctly ranked order, correctly rendered pair. And for the rest of for the rest of the data set, we do the same thing for every pair in the data. For choose 2 is 6. And for these 6 pairs, we correctly ranked 5 of them. So the concordant index will be 5/6. The higher the concordance index means like the more accurate ranking we're making for the model. So the formal definition of the concordance index is to calculate the proportion of all comparable subjects whose predicted and outcome orders are concordant with the equation I show it here. The red part represents the outcome orders or the true orders of their event times. And the green part represents the predicted orders. And basically we want the red part and the green part, their orders are concordant for every pair. And as we may recall from the first slides, second slides in the presentation, we start introducing about survival analysis by saying it is a lot like regression, right? So the only difference is the survival can have some censorship in the data set. So one natural question when people may ask is why not people use MAE or MSE as the evaluation matrix? So the MSE or MAE measures the time to event accuracy. For example, in this figure, we can see it simply measures the differences between the true times and the predicted times. And a slight digression here, in the paper, we also prove that the MAE, the absolute arrow with median survival time is a proper scoring rule, and MSE, the square arrow with mean survival time is a proper scoring rule. Here, the proper scoring rule is defined as a better model always has a better score, like the smaller score in terms of MAE or MSE. So many people think or use C-index because they think C-index is first of all useful, and people often think C-index can resemble MAE or MSE in some levels. For example, people think a model with higher Z-index should also have a better MAE or MSE score. In the paper, we actually prove that it cannot happen. But instead of some boring proof, we're going to motivate you with 3 simple examples to show that C-index and MAE or MSE are distinct concepts in model evaluation. So we start the example with 3 subjects. These 3 subjects have their true labels represented as this colorful stars, A with red and B with green and C with blue. We can see the true order of the stars is such that the red ahead of the green and ahead of the blue. So A first, B second, and C third. So we can have the first model, the model square. This model achieves the perfect C-index on its point prediction. The squares are the model's prediction time for these individuals, we can see that the order of these squares are perfectly concordant with the orders of the stars. However, as to the MAE or MSE, the distance between the square and the stars, they are relatively large. So that's why this model have a perfect C index and per MAE or MSE. And we have a second model, model diamond. So the diamond here makes the prediction, the scalar prediction at those diamond points. This diamond model achieves poor C index as the predicted order are completely reversed. It predicts the blue as the first, green as the second, and red as the third. And however, it shows some perfect MAE performance because the differences between the star and the diamonds, they are relatively small. And for the third model, we can have a model circle. This model circle achieves both perfect C index and perfect MAE and MSE. You can see the order of the circles aligns with the order of the stars, and also the distances between the circle and stars are quite small. So that's our motivating example of why C index and MAE are distinct concepts. In our paper, we actually proved MAE are distinct from all other matrix for survival analysis. For example, the IBS, the AUC, and some calibration measurements. However, due to the time constraint, I will not go through them one by one. But if you're interested, you can look our paper.
I have a question there. So your comment, yes, this slide, your comment on this slide, right? It's true even without censoring. Is that correct?
Yeah. Yeah. Well, we use this example without censoring. Yeah.
These differences work independent of censoring. It's just true even if the problem is not a survival analysis problem, it's just a traditional regression model. Is that correct?
Yeah, of course. It is suitable for regression models. Yeah. Thanks for pointing out. I will just continue. So for calculating MAE matrix for survival models, one may think it's very simple. We have the time predicted and we have the time observed, and we directly calculate the absolute difference. However, as we remember from the first slide or second slide in the presentation, we have a lot of sensor subjects in the survival dataset. For those sensor subjects, we only have a sensor time for those subjects. Those sensor time is not as informative as the event time, but it can represent of some information because it represents a lower bound of the event times. So how to get this highlighted value here, the true event time for calculating the MAE is a key question here. So there has been some solution for handling right censoring in MAE or MSE. So the first obvious naive approach is MAE uncensored. So it simply excludes all sensor subjects from the dataset and calculate the MAE score using all the uncensored subjects. So this method is obviously problematic because for many survival datasets, we can have like 50% censored subjects, or even for some extreme datasets, we can have 90 or 95% or 98%. You will see that in my later presentation, you can have 98% of censoring. So if you're going to exclude all 98% censored subjects from the dataset, you're eventually left only with 2% of the data. This obviously will introduce a strong bias to your evaluation. And the second method is called MAE hinge. it considers only if the predicted time is earlier than the sensor time. So, for example, we have two sensor cases. One is the file missing case. One is the left studying case, and we have their sensor time marked as icon here, and we have their predicted survival time as a diamond here. So for the first case, because the predicted time is earlier than the sensor time, so and sensor time is, we know, must be earlier than the event time. So we know that in this case, there must be some kind of errors between the prediction and the true times, and we can quantify that this error using the difference of the sensor time and the predicted time. And for the second time, the predicted time is after the event, the sensor time. And also because the true event time can be anywhere after the sensor time. So in this case, we don't actually know how much difference our prediction, like how much error our prediction made. So in this case, we can only give like an error of 0 in this case. And this measurement, this approach is also problematic because it considers 0 for like if the predicted time is later than the sensor time. So think about this model. This model predicts a very large time for every subject in the dataset. Then for every sensor subject, because the predicted time is always very large, so we can assume the predicted time is always later than the sensor time. So the errors for those sensor people will always be 0. In that case, this model actually hacks the MAE hinge score by providing 0 scores for every sensor subject. If, for example, the sensor proportion in the data, censoring rate in the data set is very high, 90, for example, 90, 98%, we're ending with 90% of the errors being 0, with only 2% of the real errors. In this case, we can hack the MAE hinge score by giving a very large prediction for every data set. So the first method is called the MAE margin. It's proposed by my supervisor and his former student. So this method is uses an unbiased group estimated survival distribution. This group level survival distribution is estimated by Kaplan-Meier. So as long as we observe infinity samples, we can assume this group level survival distribution is unbiased. And it is a group level distribution, so it didn't consider the effect of the covariance. And we can consider this distribution as a prior knowledge. So for the easy of the presentation, I didn't include the calculation of the Kaplan-Meier, but it is very straightforward and basically calculates at every point, calculates the proportion of at risk, proportion of happening event people divided by the at-risk people. And this curve, this estimation can serve as a prior knowledge of the survival distribution. And for a sensor people in the testing set, for example, we observe sensor people as this blue dot here, we can actually update the prior distribution to a posterior distribution. So how do we get this posterior distribution? We first plug in the sensor time to the Kaplan-Meier curve, the blue curve, and for the subsequent Kaplan-Meier curve after the censoring time, we stretch the curve or we normalize the curve to make the curve starting at 100% again. So this curve can be represented as a conditional survival distribution given a patient is censored as CI. So this orange curve is defined as this. And for this curve, we can actually calculate the area under this curve And then we can use the area under this curve as a surrogate value for calculating the MAE. So we get the surrogate values, then the surrogate value will just replace the true values for this censored people because we didn't really know the true values. So we use surrogate value instead and calculate the MAE just regularly. So, and another illustration about this surrogate value is that it can represent as the mean survival time given the sensor time. So this equation here is the time given this people is censored as CI. So in this paper, we propose 3 more novel methods, and hopefully these 3 methods can all beat the previous method. So the first method we're proposing is using the idea of IPCW. So IPCW is a little bit complex idea, but here we're just going to represent the IPCW ways using this G, and we're going to motivate the idea of IPCW. So the idea of the IPCW is to transfer a censored point's weight to the relevant uncensored subjects. So let's start with an example using 5 subjects. The greens are the uncensored subjects and the yellow are the censored subjects. And they're ordered from E0, C1, E2, E3, C4. And initially, they all have a weight of 1. Each one will consider equally in the MAE calculation. So to calculate, to approximate the error for we made for this censored people C1, we can first obtain the error of E2 and E3. So we got a 5 and 3 for those two. And we can approximate the error for C1 as the average of the subsequent uncensored subjects. So all this, as long as the data increases, the data goes to infinity, we can get unbiased estimation. So remember, initially we have everyone with a weight of 1, and right now we can consider this C1 has a weight of 0, but instead he transferred half of his weight to E2 and E3, and E2 will now have a weight of 1.5, and E3 will have a weight of 1.5 as well. So we do it for every sensor subject in the data set, and eventually we accumulate it towards the weights for the uncensored data point and calculate the score. But there is one obvious flaw for this evaluation, because we estimate the error for C1 using the errors for others. So we didn't use the true values of true event times for C1 because we didn't know that. However, we didn't use the predicted event time for C1 as well. This motivates the second method. This is called IPCWT. The previous one is called IPCWD. D stands for the differences, and T here stands for the time. So you can tell from the name that we're gonna use calculate a surrogate value just like the MAE margin, the MAE margin way that we did, and we're going to calculate the surrogate value of the C1 using the average of its subsequent event people. So for example, the event of 2 and 3 are 20 and 24. Then we can calculate the surrogate value for C1 using the average of the two. So, and once we calculate the surrogate value, we can just doing the same thing as MAE margin, we can calculate the absolute value between the surrogate value and the predicted values. And the last one is we find most effective and more interesting. So this one is also a decensoring method, which means it's also calculates a surrogate value for every sensor subjects. it calculates the surrogate value using the idea of pseudo observations. So if people familiar with the sampling techniques, there is a kind of sampling techniques called the jackknife method. So this pseudo observation method is a lot like inspired by the jackknife method. So give you a toy example of how does it do the calculation. It calculates how much a sensor subject contributes to the Shi-ang curve. That means for the same example we have earlier with the 5 subjects, we first calculate the Kaplan-Meier curve for the 5 subjects for the whole group first. When we end up getting this red curve, and we can calculate, for example, the mean survival time for this Kaplan-Meier curve, the area under the curve. And then, because our target is to estimate the surrogate value for C1, we can then exclude C1 from this calculation and calculate the Kaplan-Meier curve for the rest of the 4 points. So the new Kaplan-Meier curve without C1 will be this blue curve. And we can also calculate the statistic for this blue curve, and it ends up with a mean survival time of 10. And we can compare those 2 curves and plug into this equation. Here, the red value is the mean survival time for the whole 5 points, and the blue is the mean survival time for the 4 points, excluding the CI. And N here, because we have 5 subjects here, so N will be 5. When plug in this equation, we end up getting a surrogate value of 12.3 for these subjects. And in theory, in this paper, we also provide a theory about the authenticity about this pseudo observation values. So we prove that the pseudo observation values is always larger than the survival sensor time, because the event time should always greater than the sensor time for the sensor people. So our estimated event time should also have the same property. Okay, so above those 6 methods, 3 of them are calculating the surrogate value for the sensor subjects. We call them desensoring techniques. For those desensoring techniques, we also apply the weighting scheme. This weighting scheme represents our level of confidence of those surrogate values. So, for example, for uncensored subjects, we didn't calculate the surrogate values. We directly using the true event times for those uncensored subjects. So we can apply a weight of 1 for those uncensored subjects. For the censored subjects, we motivate the weighting. The weighting should be 1 minus the Km curve. So the Km curve is the blue curve, and the 1 minus the Km curve should be this brown curve. So what's the property of this brown curve? The property of this brown curve is it is going to be small for early sensing subject and large for late sensor subjects. So this weighting, for example, if a people is censored at time 0, censored at time 0 means his or her event time can be any time lying between time 0 to time 3, right? So this censoring time at 0 is really not informatic at all. So we should have very minimum confidence at the surrogate value that we estimated. So for another example, people censor at 2, the true event time can be anywhere between time 2 to time 3, and makes the censoring time more informatic, and we can believe more about our surrogate values. So that's why the weight should be small for earlier sensing subjects and large for later sensing subjects. Okay, that's the first contribution of our paper, the development of MAE PO method. and applying a weighting scheme to the evaluation matrix. So for now, any question? Okay.
Questions?
Then I will just start. Keep going. So
I have one actually. It's just related to. So you said you're concentrating on the MAE, but you have results also on other metrics. So do you? Let me rephrase the question. Is there a reason for which you concentrate on MAE and not on MSE?
So you can choose MAE or MSE. They are both purple scoring rule as our theorem in the paper provides. So this theorem, they're both purple scoring rules, so you can choose either of them. But if you are using median survival time, you should compare it with MAE. But if you are using mean survival time, then you can like using MSE. And in most cases, people use median survival time because for many cases, for example, the predicted ISD curve doesn't crosses the 50% quantile line, the horizontal line. So we don't know, so for many cases, the ISD curve didn't end at 0. So we cannot calculate the mean survival time properly. But if as long as the curve crosses the 50% line, we can calculate the mean survival time. So in medium survival time is better than mean survival time. So that's why we propose MAE is better than MSE.
Thank you.
Okay, so our next objective is to find which MAE variant is the best. So we have 6 of them, 6 MAE variants. Our objective is to rank the model correctly as the true MAE and also closely resembles to the true MAE. So how can we do that? We can only do that if we have the true event time. However, in the real world survival data set, we don't have that. So our second contribution is that we propose a way to create realistic semi-synthetic data set. Here, the realistics means we have the real features, the real event time, and close to real sensor times. So we started with a real data set. There's a B with greens as the event uncensored people and the yellow as the censored people. The first step, we're going to remove censored subjects, remove the yellow dots in the data set, and this gave us the data set of B prime. And the second step, we're going to create some synthetic censorship points for every subject in the data set. So we can use, for example, a uniform distribution. This is a very naive way. The uniform distribution can start with 0 and end with the maximum time of the data set. And for every data in the D prime, we're gonna sample synthetic sensor time for the data. And if the synthetic sensor time is ahead of the true event times, we artificially censor the people. If not, if the yellow dots are after the green dot, we do nothing to those people. We keep them as uncensored. So this is called semi-synthetic data set, and we label them as D double prime. So after we get this semi-synthetic data set D double prime, we can evaluate. We can train a learner and get a prediction from the learner, and then we can calculate the MAE variance scores using the semi-synthetic labels and the predicted values to calculate the MAE variance score. In the meantime, we can also calculate the true MAE using the true labels. Here, the true label means the before artificial censoring labels. So we'll use true labels for those people and calculate the true MAE between the true labels and the predictions. And the next step, we're going to compare the MAE variance with the true MAE, see whether they can rank the survival models correctly and whether they can have the similar score as the true ME. So the above case uses a very simple idea of uniform censoring, right? It is very naive and stupid. Many people may argue that it is not a close to reality sensor distribution. So to make it more interesting, we can add different type of sensor distribution. For example, we can add the uniform and administrative censoring. That means uniform distribution. We manually truncated them at a predefined time. And we can also have exponential distribution. And we can have something called original distribution. This makes things very interesting here. We can get the original data set and we can flip the data set, flip the sensor bit of the data set, and estimate the sensor distribution from the data set using the Kaplan-Meier. This sensor distribution didn't consider the effect of the covariance, so we call this distribution as the original distribution, as it replicates the original sensor distribution in the data set, and independent of the covariance. Then we can naturally think about doing an original but dependent censoring, which considering the effect of the covariance, we can building this sensor probability, sensor distribution using any survival models. In the experiment, we're using Cox proportional hazard to considering the effect of the covariance. And lastly, we can do more interesting things. We can bring in an external data set and we can estimate the sensor distribution for that external data set. And this distribution we call it external distributions. So all these three synthetic sensoring distribution, they are all calculated from the real world data set and drawn from the real distribution. So it is the close to reality distribution. And remember, our data sets didn't modify the X and T's, so it also has the real features and the real event times. So that's why our semi-synthetic data set is realistic. So to recap, we start with our real survival data set, and we create deep prime by removing sensor subject, and create the double prime artificially censored those subjects using a very novel idea of synthetic censoring. And we consider a set of IC algorithm or survival algorithm. And for each data, D prime and each algorithm, we calculate a model using MAE variance. So the question left which survival data set we use and which algorithm we use. So the survival data set we use contains 5 public survival data sets.
So I have a question about this procedure of creating a synthetic data set. So this is always under the assumption on independent censoring. Is that correct?
Yeah. That's again, it's a reasonable assumption. Every people, like most people in survival domain, use that assumption. Like for example, the Kaplan-Meier estimation, it is unbiased only if the independent censoring assumption is true. So this is a very reasonable assumption, and but in the future we can also expand this assumption to like dependent censoring assumption to make things more interesting. So about the data sets, we choose 5 data sets and with a lot of variety. So for example, the sensor percentage, we choose the data set ranges from 70% to 97%, and the number of events ranges from a few hundred to 12,000, and the features ranging from 9 to 91. And for the survival models, we use 8 survival models, starting from the oldest Cox proportional hazard model to the very latest survival mixture density networks. And we also include 2 dummy models. So the dummy models will be linear regression, the LR, because it is a regression model. It doesn't know how to handle the sensor subjects. So to train the model, we simply drop the data set from the training set to make it happen. And another dummy model would be the Kaplan-Meier models. So the Kaplan-Meier model is a group level survival prediction models. It didn't provide individual effects, the effect of the covariance. So the survival curve will be identical for all the testing sets. So we include those dummy models because also the variety of the survival baseline. We anticipate that these two dummy models should perform very bad in basically every cases. And we hope like some models can be better and some models can be worse, and our MAE measurements can able to discriminate them. So again, our objective for a good evaluation metrics is that a good metrics should accurately rank the performance of a learner, which is discrimination, and it should also closely approximate the true MAE, which is a calibration aspect. So a first example comes from this GBM dataset uniform with administrative censoring distribution. This synthetic, a semi-synthetic dataset has 54% of censoring rate. And in this figure, we have two y-axes. The left one is the ranking, the right one is proximity to the true MAE. So as to the ranking, we're looking at the dots of the true MAE. The true MAE orders the 10 survival models from the top to the bottom. And for the first three models, for the top three models, we use the solid dot and with gradually decreasing sizes for the orders, based on the orders. And basically, we hope the best MAE metrics can also identify the top three models as to the true MAE. So in here, you can see that the PO, the pseudo observation variant of the MAE, it is the only metrics that can correctly rank the order of the top three. Others will have some errors. For example, those IPCW and the uncensored, they can have a lot of error in ranking the people. And why the top three models? Because in most real world applications, we only care which models are the best, or like the top of the best. So that's why we only care about the top three. And for the second objective is proximity to the true MAE. The matrix with smaller error bars have the better performance. As we can see that the pseudo observation has the smallest error to the true MAE. And if you are considering the error bars, this difference is quite significant. And the results, this is another result from the meta-brick dataset using the original distribution independent of the covariance. This ended up with 20% of sensing rate. And as we can see in this example, the margin and the PO, the pseudo observation, can both correctly rank the top three models. They both have the three solid dots in the box. And however, pseudo observation MAE has a slightly smaller error to the true MAE compared to the margin. The error bars is the lowest among the all six, so that we can still say the pseudo observation is better than margin because it's more close to the true MAE. So we have so many data sets and so many synthetic censorship. In total, we have 29 data sets, and we can have a summary of the empirical comparison is that the MAE pseudo observation is the best among 22 of them, and margin is the best among for the rest of it. And we observe that the margin is especially useful for exponential distribution. However, the pseudo observation significantly outperforms all other measurements, which makes we should believe that the MEPO will be an effective measurement for the survival performance. So conclusion, the MAE and MAC is fundamentally different from the other metrics. And we propose an MAE-inspired evaluation matrix using the pseudo observation and conservative rating. And we provide a way to evaluate the survival matrix by generating a realistic semi-synthetic survival dataset. And in most situations, the MAE pseudo observation is better in terms of both ranking the models and resembling the true MAE. And so for some further directions, one of them, Alexandra just asked, is to extend the MAE measurement beyond the independent sensory assumption. And the second direction will be like beyond the rest sensory. There is left sensory cases and interval sensory cases. And at the end of the presentation, I want to introduce you to one of my developed package. It's a Python package for evaluating the survival models. It's a comprehensive package that includes all kind of the measurements that I present in the previous slides. So a little bit comparison about my package with the existing survival package. You can see my package is the only one that includes MAE or MSE measurement and includes 2 calibration measurements on top of the four regular metrics that other package does. So if you want to use this handful package, you can just scan this QR code. And thanks for listening for my presentation. And if you want for more empirical results or theoretical results, you can read the paper. The paper code, the QR code is at here. Yeah. And that's the end of my presentation. Thank you.
Thank Shi-ang for the great talk. So I have some questions. But let's see So Dr. Zubovic. We can't hear you. Yes.
How can I see the chat? But
Chat?
I mean, how can I see the chat like Zoom?
I'll take care of that.
Okay.
Yeah. Okay. Microphone is not working. So let me check. Oops, what happened? So Dr. Zubovic has this question. Could you tell us what motivated you to use the pseudo observation approach?
Yeah. So in the presentation, I kind of motivated. So the idea of pseudo observation is to calculate how much a sensor subject contributes to the group level estimation. So it's basically like in the BRACKNet sampling method, we're estimating the group mean, and where we can eliminate one people from the estimation and see how much it can contribute to the group level mean. And so that's the inspiration of the pseudo observation. And for why I use pseudo observation in the MAE matrix is simply because it is the best effective method compared to all of these variants. Basically, this project goes on and on, like quite a lot of times. We started with margin and then we start with MAE IPCW and find out they didn't quite work. And eventually we come up with this idea and find out it eventually works. And I'm glad this simple and easy to interpret method is working.
Other questions? So I have a question. So I would say maybe go to your last slides, the slides on conclusions and on previous slide. Yeah, okay. Yeah, keep going. Yeah. Yeah, okay. So that's okay. So I would say the C index in itself answers the questions related to if I have an organ, do I have to give the organ to this person or to this other person, right? So what I'm saying here is that like it seems to me that there is a dependency on the question, right?
Yeah.
So if the question is who do I have to give the organ to, then and the interest of the doctors is just enough 1 second of life more, then the rule says we give the organ to this person. And then at the point you care about the C index.
Yeah.
Which might mess completely up the distribution or the survival distribution. But for that criterion, that's what they care about, right? So I would say the metric depends on the metrics you use has large dependence on the question that you want to answer, right? What are your thoughts about that?
Yeah, exactly. In the from the application side of the wheel, which evaluation matrix to choose purely depend on the which application that you're using. If your application involves with ranking people, selecting people from a pool of subjects, selecting the like prioritizing the people, then C index we won't argue with you. C index is the best suitable metrics for your application. However, in more applications, we find that making individual level decision is important. For example, individual level decision could be based on the, for example, if the survival time, if the predicted survival time is less than 1 year, that means these people has a very high risk, high probability of dying in the next year, then we should probably give him or her some like high risk surgery to make magic happen. Or if the predicted survival time is very far away from now, for example, 20 or 30 years from now, then we can choose some conservative surgeries to like not high risk surgery to like keep the survival curve still very low risk, and that's the motivation of individual level decision. We make the decision only based on the prediction of that patient. So in this case, the accurate of this point prediction is important, and that's MAE and MSE is important. So yeah, if you're using C index, you better using like ranking people. And from the theoretical side of the wheel, I believe, and our research team believe, if you're building a foundation survival algorithm, then you should use MAE and MSE as your evaluation matrix, because you should be comparing all aspects of the models. Yeah.
Awesome. All right. So guess no raised hands. So no other questions. So let's thank Shi-ang again for the great presentation. Thanks a lot for sharing your work with us.
Thank you, Alexander, for having me.
My pleasure. All right.
Okay.